Okay, our last speaker of the session is Katherine Glasheen, presenting Improving Understanding and Forecasting of Tornado Formation using Networked Small Arrays.
Thank you for the introduction. So tornadoes cause extreme devastation in terms of millions of dollars, in terms of fatalities. In the last decade, there have been thousands of tornadoes in the United States alone, which has caused about 1,000 deaths. And the most extreme tornadoes that we see come from supercell thunderstorms. The current method of issuing tornado warnings is called warn on detection, and that basically means that a warning is issued once the tornado is actually detected, either visually or early signs on the radar. But this only provides about 13 to 17 minutes of advance warning before the tornado actually strikes. The weather forecasting community believes that if we have more data, we can create better models, and these weather models can then create more accurate forecasts, which will help us identify where a tornado is going to hit hours in advance. In order to get more data, a good platform is Small Unmanned Aircraft Systems, or SUAS. And this kind of aligns with what Mark from NOAA was saying yesterday, where you can have radar data and other tools. I think in his context it was satellites. But if you get information actually in the storm, just like his gliders on the surface of the oceans, you can get a lot richer of a data set that will help you predict better and just give you a better picture of what's actually happening. And using small unmanned aircraft systems or other mobile sensors and actually getting those data into weather forecasts in real time is a near future reality due to the current state of the art of network connectivity and cloud computing. So that's where this work comes in. Our project goals are twofold. First, we are designing a system to plan safe trajectories for small unmanned aircraft systems to fly through uncertain atmospheric conditions. And that's anything from extreme tornadoes to flying in urban environments with an uncertain wind field. The second goal is to develop a closed-loop architecture where the observations from these small unmanned aircraft systems can be sent to dispersed computers, where they then can be integrated into weather models to update the forecasts in real time, to then be used again by the small unmanned aircraft systems for path planning. So what does this dispersed architecture, dispersed computation actually look like? So we already have a lot of computers that exist in many different formats. We have computers on our vehicles. We have computers in high-performance computation centers. We have computers that store data that we can access on the World Wide Web. And even though all of these computers can exist through a network connection, we need a specific component in order to get these computers and this data to actually talk to each other and be accessible. And that is where the resource manager comes in, the block you see in green on those different computers. And the resource manager is a software component that we consider the gatekeeper of the specific computer that it lives on. So in the context of an SUAS, the resource manager can request maybe a path through an uncertain environment. And that resource manager in the ground vehicle in the corner can then accept that request and then search for the information it needs, engage the right planners and the right computation resources to then send a path back up to the resource manager on the SUAS. But how do we actually plan safe paths through uncertain environments? This work uses the Rapidly Exploring Random Tree, or RRT class of algorithms, which in themselves, they're very simple algorithms. They basically have two steps. First, the algorithm samples a node in the problem space, and then it employs an extend function to literally extend the vehicle's position and add that node to the search tree, like you see on the side. Now what we do is we formulate the planning problem into a chance constraint problem. And so what this means is that we're defining the probability of safety as a constraint when we use the RRT algorithm. So what does this actually look like? The sampling step is the same, sample a node in the problem space. But then when we extend that node, or extend the tree to include that node, what we do is we realize the uncertainty in the environment thousands of times and employ a Monte Carlo simulation where we're extending that tree to include that node under all of these different realizations. And then what we can do is, since it's sampling based, we can simply count the edges between those two nodes that are in collision with obstacles, and that's how we back out our probability of safety. So the new node will only be added to the search tree if the probability of safety is acceptably high. If it's not acceptably high, we simply throw away that node and resample a new node. And this process continues until the goal region is reached. All right, so what does this actually look like when we put it all together? So here we have a small unmanned aircraft system trying to fly through an extremely uncertain environment. And what it can do is reach down to a resource manager. Maybe it's located in a city far away. Maybe it's a ground vehicle in an experimental van close by. But it sends its request for a path and also its most recent observations to that resource manager. When a resource manager accepts that request, it can then search around on the internet and pull a weather model from a forecast database. It also then sends the observations that it received from the SUAS to a supercomputer where the weather forecast models are being run and updated, and then the output of that can be stored back into the weather forecast database. Then the resource manager searches around for our Monte Carlo RRT path planner and engages the path planner using the mission specifications and the weather model that it just pulled. And now this Monte Carlo path planner, because it's located off board, it can be parallelized. This extension process that I just described in the last slide can be run simultaneously on many different threads and cores to speed up the computation process. And the output of that is a planned path, which is then sent back to the resource manager, which then sends that path back to the SUAS to fly. Now this process does happen in a receding horizon fashion, which means that as the aircraft is flying this solution, it will repeat this process and re-request a path from a resource manager in order to get the most updated weather information and the safest path possible at all times. So some experiments that we've done in simulation, excuse me, I'm losing my voice and trying to get it back, so I apologize. So what we did for this experiment that you see on the top, the path planner was engaged using a probability of safety over each edge and over the entire path. So we restricted the probability of each edge, so that's the area between two green nodes in the image, to be 99.5% safe. And then we restricted the probability of the entire path to be 95% safe. And we employed a simple Dubin's-Carr dynamics model to actually simulate the aircraft's behavior as it flies through a wind field, which we simulated as just a normal distribution from a forecast at 50 meters resolution. And then we added some error due to interpolation and just general forecast error. And the output of that path, which you see in black on the bottom, was then sent to a closed-loop aircraft simulation, which was commanded by an autopilot and then guided by an L1 guidance method, which fed course rate commands to that autopilot. And simulations were run with this closed-loop autopilot under the same wind field parameters with different uncertainty conditions. We no longer have interpolation uncertainty because we're assuming the aircraft gets a measurement at each point. So anyway, the outputs that you see are in color on that same bottom graph, and 100% of those trajectories that this closed-loop simulation flew did not crash with any obstacle. However, there are some interesting characteristics of the path and the result that are worth noting. First of all, the path gets, in my opinion, uncomfortably close to one of the obstacles that you see. It's kind of following this straight line, and then once it starts curving, it's very close to that obstacle. And this could be due to the assumption that the planner's making. So you'll see in the top image that every time we extend between two nodes, there's a distribution of end states. However, then the planner collapses that distribution to the mean of those endpoints, and then the next edge is simulated assuming that all of the edges start from that one point. And this is just causing a lot of lost information. So that could be an issue why the planner is characterizing these points as safe when they're so close to obstacles. Another thing to note is that there's a lot of overshoot on our path, and this is totally fine in this context, but what we would expect to see is that the planned path is kind of in the middle of all of these simulations, given that it did account for all these different cases of uncertainty. And this could be just due to using a very simple dynamics model. Our path planner basically abstracts everything below the guidance level, and it just might not be capturing the right behavior that a 12-state nonlinear aircraft dynamics model actually experiences. So there's some room to kind of keep tuning and play around and understand these results a little bit better. So as we're developing these algorithms in simulation, we're also working on field campaigns and developing up our field systems. Currently, we're in a campaign that lasts over 2 years. It's called Project Taurus, targeted observations by radar and UAS of supercells. And so the campaign itself stretches over 2 years, but it consists of 2 5-week deployments, which the deployments are across the entire Great Plains. We have certifications to operate in many different states, and we basically just deploy and go nomadic and try to target these storms for data. And in our last campaign, which happened in May, the first 5 weeks, we flew 4 of our Raven aircraft, and we actually flew in 5 supercell thunderstorms that produced tornadoes. So we assume that we have a lot of very rich data sets, and so currently we're sending that data over to the meteorologists to just better understand what's happening and hopefully get a better understanding of these, how to create these weather models. Another important field system that we have is our MERC vehicle, our Mobile UAS Research Laboratory. And this is just a big old van with a lot of really intense computation power. And so the idea is that we can take this to the field and actually house like a resource manager and these path planners on the vehicle, and then the aircraft can reach down and kind of use that vehicle as a node to either do the computation right in the vehicle or have that outsourced and reach back to some other resource manager elsewhere to get the data that it needs and run the algorithms. And with that, thank you for listening, and I'll open it up for questions.
Questions for the speaker?
Okay. What is your planning horizons or lag and update frequency in the system?
So all those parameters really depend on what the mission is and how variable the environment is. And I think that that's actually one of the challenges with using these sampling-based planning algorithms is that because it randomly samples the nodes in space, like the time to generate a plan scales with the complexity of the environment, but there's enough randomness where it becomes a tricky problem actually to determine what your planning horizon should be and just how all those horizons kind of fit together and what the lag is going to be when you're sending the path. So that's TBD, but it's actually a very complex problem.
What did you use so far?
So far? So I think that in our last campaign, we were flying in Pawnee National Grasslands, which is just a big open area, and we were flying like a 4 mile by 4 mile radius on a windy but fairly clear day. And I think it was on the order of maybe, like we planned for 30 seconds, and then we follow the path for 10 or 15 before sending a new plan. But that's when we, I guess, kind of uncovered the complexity in this kind of system and how those details actually matter. So yeah, it wasn't always successful.
Any other questions?
Hi, you talked about different levels of safety in your path planning. Could you describe briefly what it would be like to have an unsafe path plan, and then what contingencies you have if you encounter that?
Yeah, that's a really good question. So the best example of an unsafe path is one that crashes into, say, a building. I think that's the least ambiguous case. And that's a really good question. I think that we heard yesterday that using sensors and then updating your path based on your sensor readings is not always realistic, especially when you're flying a fixed-wing aircraft in a tight environment like a city. So I think that it really, like what I'm thinking about right now in terms of like how to think about that scenario would be to basically have kind of escape routes that I would employ. Like if there was an issue where the aircraft realizes that it's about to hit an obstacle, like kind of predefine loiter routes along that path so that the aircraft can at least like try its best to deviate and get into a loiter in time for it to be sent to a new path. So something kind of like that for now. Because it's really challenging when flying fixed wing aircraft. It's not like a quad where you can just stop and kind of hang out, so.
Let's thank the speaker one last time.